Hello and welcome to Polarify Consulting. In today's video, we will discover how nanotechnology is impacting the semiconductor industry. From the dawn of civilization to the information age, humanity's progress has always been intertwined with our mastery of materials. We've journeyed from crude stone tools to the intricate circuits etched onto silicon wafers, each leap driven by our insatiable curiosity to delve deeper, to manipulate the building blocks of matter itself. Today, we stand at the cusp of a new era, the era of nanotechnology, where we orchestrate the dance of atoms and molecules with unprecedented precision. In this quantum realm where the familiar laws of physics yield to a new set of rules, lies the key to unlocking a future of boundless possibilities. Join me as we embark on an exhilarating expedition into the heart of the nanotech revolution, where we'll explore its profound implications for one of the most transformative inventions of our time, the semiconductor. Together, we'll traverse the cutting-edge laboratories and research institutions at the forefront of this technological renaissance, meeting the brilliant minds who are shaping the future of our digital world. Imagine a world where electronics operate flawlessly in the most extreme environments imaginable, from the scorching heat of a volcanic vent to the frigid expanse of outer space. This is the promise of high-temperature electronics, a field undergoing a revolution thanks to the remarkable properties of materials like gallium nitride, or GaN. JN, a compound of gallium and nitrogen, stands as a shining example of how we can harness the power of nanotechnology to transcend the limitations of traditional silicon-based electronics. With its ability to withstand temperatures that would melt conventional circuits, GaN opens up a realm of possibilities previously confined to the realm of science fiction. Think of the implications for space exploration, where spacecraft must endure the unforgiving cold of deep space and the scorching heat of atmospheric re-entry. GaN-based electronics could power future rovers exploring the searing surface of Venus, or probes diving through the icy plumes of Europa, a moon of Jupiter thought to harbor a hidden ocean beneath its frozen shell. But the benefits of GaN extend far beyond the final frontier. Picture a world where electric vehicles charge in minutes instead of hours, their power electronics operating at significantly higher temperatures and efficiencies. Imagine a future where data centers, the backbone of our digital lives, consume a fraction of the energy they do today, their servers humming along, powered by GaN transistors that dissipate heat with unparalleled ease. This is not a distant dream, but a rapidly approaching reality, driven by the relentless pace of innovation in nanotechnology. Researchers and engineers are continuously pushing the boundaries of GaN-based devices, developing new techniques to grow high-quality crystals, optimize device architectures, and unlock the full potential of this game-changing material. From power grids to telecommunications, from healthcare to manufacturing, the applications of high-temperature electronics are as diverse as they are transformative. As we delve deeper into the nano world, we unlock new possibilities for creating a future where electronics are not only more powerful and efficient, but also more resilient and adaptable to the challenges of our ever-changing world. The journey from a brilliant idea to a tangible technological breakthrough requires more than just scientific ingenuity. It demands collaboration, shared resources, and a spirit of open innovation. In the realm of nanotechnology, this collaborative spirit finds its embodiment in advanced nanofabrication centers, where the world's leading researchers and industry pioneers converge to push the boundaries of what's possible. These state-of-the-art facilities serve as crucibles of innovation, equipped with an arsenal of sophisticated tools and instruments capable of manipulating matter at the atomic scale. Here, electron beams dance across surfaces, etching intricate patterns onto silicon wafers with nanometer precision. High-powered lasers flash for billionths of a second, depositing ultra-thin films of exotic materials with atomic layer control. But it's not just about the tools, it's about the people who wield them. Nanofabrication centers act as magnets for the brightest minds in materials, science, physics, chemistry, and engineering, drawing together experts from diverse disciplines to tackle some of the most challenging problems in nanotechnology. Imagine a team of physicists working alongside materials scientists to develop new techniques for growing ultra-pure, defect-free Jiang crystals, the foundation upon which high-temperature electronics are built. Picture chemists collaborating with electrical engineers to synthesize novel polymers with tailored electrical properties, paving the way for flexible and transparent electronics that can be seamlessly integrated into our lives. This interdisciplinary approach is crucial for driving innovation in nanotechnology, where breakthroughs often occur at the intersection of multiple fields. By fostering a collaborative environment, nanofabrication centers act as incubators for groundbreaking discoveries, accelerating the translation of scientific knowledge into tangible technological advancements. Moreover, these centers play a vital role in bridging the gap between academia and industry, facilitating the transfer of cutting-edge research from the laboratory to the marketplace. By providing access to their world-class facilities and expertise, nanofabrication centers empower startups and established companies alike to develop and commercialize next-generation technologies. This symbiotic relationship between research and industry is essential for driving economic growth and societal progress. As nanotechnology continues to revolutionize industries from healthcare to energy, from computing to manufacturing, the role of nanofabrication centers in fostering innovation and collaboration will only become more crucial. These centers serve as vibrant hubs of knowledge exchange, where researchers from different institutions and companies can share their expertise, learn from one another, and forge new partnerships that accelerate the pace of discovery. In the relentless pursuit of faster, smaller, and more powerful electronics, we find ourselves constantly pushing the limits of what's physically possible. As traditional silicon-based transistors approach their fundamental limits, a new wave of nanoelectronic devices emerges, promising to revolutionize the way we compute, communicate, and interact with the world around us. Imagine a world where computers are no longer confined to rigid circuit boards, but woven into the very fabric of our clothing, monitoring our health, providing real-time information, and connecting us seamlessly to the digital realm. Picture a future where sensors, smaller than a grain of sand, are deployed by the millions to monitor our environment, track the spread of diseases, and optimize agricultural yields. This is the promise of nanoelectronics, where devices are crafted from materials with astonishing properties, enabling unprecedented levels of miniaturization, performance, and energy efficiency. At the heart of this revolution lies the exploration of novel materials like graphene, carbon nanotubes, and nanowires, each possessing unique characteristics that can be harnessed to create electronic devices with unparalleled capabilities. Graphene, for instance, a single layer of carbon atoms arranged in a hexagonal lattice, exhibits exceptional electrical conductivity, mechanical strength, and thermal stability, making it an ideal candidate for next-generation transistors, sensors, and flexible displays. Carbon nanotubes, cylindrical structures of carbon atoms just a few nanometers in diameter, possess remarkable tensile strength and can act as both conductors and semiconductors, opening up new possibilities for nanoscale electronics and energy storage. But the true power of nanoelectronics lies not just in the materials themselves, but in our ability to assemble them into complex three-dimensional architectures known as 3D integrated circuits. By stacking multiple layers of transistors and interconnects on top of one another, we can dramatically increase the density of electronic components within a given space, leading to smaller, faster, and more energy-efficient devices. This paradigm shift in chip design presents both challenges and opportunities. On the one hand, it requires the development of new fabrication techniques capable of precisely depositing and patterning materials at the nanoscale in 3 dimensions. On the other hand, it opens up a realm of possibilities for creating truly innovative electronic systems with unprecedented levels of functionality and performance. Imagine a future where smartphones are no longer limited by the size of their batteries, but instead powered by energy harvested from their surroundings, thanks to integrated nanoscale solar cells and energy harvesters. Picture a world where medical implants, smaller than a grain of rice, can monitor vital signs, deliver targeted drug therapies, and even stimulate tissue regeneration, all while communicating wirelessly with external devices. The journey towards this nanoelectronic future is paved with challenges, but the potential rewards are immense. As we continue to explore the fundamental properties of matter at the nanoscale and develop new techniques for manipulating these building blocks of our universe. We unlock the door to a future where electronics are not just smaller and faster, but also seamlessly integrated into every aspect of our lives, enhancing our capabilities and expanding the horizons of human ingenuity. The development of 3D integrated circuits requires overcoming significant technical hurdles. One such challenge is heat dissipation. As transistors are packed closer together, the heat generated by their operation becomes more difficult to manage, potentially leading to performance degradation and device failure. Researchers are actively exploring novel cooling solutions, such as nanoscale heat sinks and thermal interface materials, to address this critical issue. Another challenge lies in the development of new interconnection technologies capable of reliably transmitting signals between different layers of a 3D integrated circuit. Traditional wire bonding techniques are ill-suited for the nanoscale, prompting researchers to explore alternative approaches such as through silicon vias, TSVs, and wireless interconnects to enable high-density, high-bandwidth communication within these complex chip architectures. Despite these challenges, the potential benefits of 3D integration are too compelling to ignore. By breaking free from the constraints of two-dimensional chip design, we can create electronic systems with unparalleled levels of performance, energy efficiency, and functionality. The realization of this vision will require continued collaboration between materials scientists, device engineers, and fabrication experts, all working in concert to push the boundaries of what's possible in the realm of nanoelectronics. In an era defined by our insatiable appetite for data, the energy consumption of our digital infrastructure has become a pressing global concern. Data centers, the powerhouses of the internet, consume vast amounts of electricity, contributing significantly to our carbon footprint and straining our planet's resources. The pursuit of energy-efficient hardware systems is no longer just a technological challenge, but an environmental imperative. Fortunately, the same nanotechnological advancements driving the miniaturization and performance of electronic devices also hold the key to unlocking unprecedented levels of energy efficiency. By manipulating materials at the atomic scale, researchers are developing novel transistors, memory devices, and interconnects that consume significantly less power than their traditional counterparts. One promising avenue of exploration lies in the development of low-power transistors that require significantly less energy to switch between on and off states, the fundamental operation underlying all digital logic. Traditional silicon-based transistors suffer from leakage currents, where a small amount of current flows even when the transistor is in its off state, leading to wasted energy. Researchers are exploring alternative materials such as carbon nanotubes and nanowires to create transistors with significantly lower leakage currents, reducing power consumption without sacrificing performance. These nanoscale transistors can be densely packed together, enabling the creation of more energy-efficient processors and memory chips. Another area of focus is the development of non-volatile memory technologies that retain their stored information even when power is removed. Unlike traditional RAM, which requires a constant flow of electricity to maintain its data, non-volatile memory such as flash memory used in SSDs can store data without consuming power. Researchers are exploring novel non-volatile memory technologies such as resistive RAM, RRAM, and phase change memory, PCM, which offer even faster switching speeds, higher endurance, and lower power consumption than existing flash memory. These advancements could lead to the development of computers and smartphones that boot up instantly, consume significantly less power, and have significantly longer battery life. Beyond individual components, researchers are also exploring architectural innovations at the system level to further enhance energy efficiency. One such approach is neuromorphic computing, which draws inspiration from the structure and function of the human brain to create more efficient computing architectures. Neuromorphic chips utilize artificial synapses and neurons to process information in a massively parallel and event-driven manner, mimicking the brain's ability to perform complex tasks with remarkable energy efficiency. These chips excel at pattern recognition, sensory processing, and other tasks that are computationally expensive for traditional computers, making them ideal candidates for applications such as image recognition, natural language processing, and autonomous driving. The quest for energy-efficient hardware systems is a multifaceted challenge that demands innovation at all levels, from materials and devices to system architecture and software design. By embracing a holistic approach and fostering collaboration between researchers, engineers, and policymakers, we can create a future where our digital infrastructure not only meets our growing computational demands, but does so in a way that is sustainable, equitable, and beneficial to both humanity and the planet. The benefits of energy-efficient hardware extend far beyond reduced electricity bills and a smaller carbon footprint. In developing countries, where access to reliable electricity can be limited, energy-efficient computing devices can bridge the digital divide, empowering communities with access to education, healthcare, and economic opportunities. Moreover, the development of low-power, energy-autonomous sensors and devices is enabling the rise of the Internet of Things, IoT, where billions of interconnected devices collect and share data, transforming industries ranging from agriculture and manufacturing to transportation and healthcare. Energy-efficient hardware is essential for realizing the full potential of the IoT while minimizing its environmental impact. As we stand at the cusp of a new era of computing, characterized by unprecedented levels of connectivity, data generation, and artificial intelligence, the need for energy-efficient hardware systems has never been greater. The remarkable advancements in nanotechnology we've explored so far would not be possible without the existence of sophisticated nanofabrication facilities. These cutting-edge laboratories, often housed within universities and national research institutions, serve as the engine rooms of the nanotech revolution, providing the tools, expertise, and collaborative environment necessary to transform groundbreaking ideas into tangible realities. Stepping inside a nanofabrication facility is akin to entering a realm where the impossible becomes possible. Here, within ultra-clean environments known as clean rooms, air is meticulously filtered to remove even the tiniest dust particles, ensuring that the delicate processes of manipulating matter at the atomic scale are not compromised. Imagine a symphony of advanced instruments, each playing a crucial role in the orchestration of nanoscale fabrication. Electron beam lithography systems, resembling giant microscopes, focus beams of electrons with nanometer precision, etching intricate patterns onto silicon wafers, the canvases upon which integrated circuits are born. Sputtering systems, resembling miniature spaceships, bombard targets of exotic materials with ions, releasing atoms that deposit onto substrates, creating ultra-thin films with atomic layer control. Chemical vapor deposition furnaces, resembling high-tech ovens, transform gaseous precursors into solid materials, depositing layers of insulators, conductors, and semiconductors with exceptional uniformity and purity. But it's not just the tools that make these facilities so remarkable. It's the people who operate them. Highly skilled technicians and engineers, trained in the art of nanofabrication, work tirelessly to maintain the pristine conditions of the clean room, calibrate the instruments with meticulous precision, and ensure that researchers have the support they need to conduct their experiments successfully. These facilities act as magnets, attracting some of the brightest minds in science and engineering from around the globe. Physicists, chemists, materials scientists, and electrical engineers converge in these collaborative spaces, united by a shared passion for pushing the boundaries of knowledge and creating technologies that can address some of the world's most pressing challenges. The impact of nanofabrication facilities extends far beyond the walls of their clean rooms. They serve as catalysts for innovation, driving economic growth, creating high-skilled jobs, and fostering a culture of scientific inquiry and technological advancement. By providing access to their world-class resources and expertise, these facilities empower researchers from both academia and industry to pursue ambitious projects that would otherwise be impossible. Startups, often born from groundbreaking research conducted within universities, rely heavily on the resources and expertise available at nanofabrication facilities to develop and commercialize their technologies. These facilities provide a crucial stepping stone for young companies, enabling them to scale up their production processes, refine their prototypes, and ultimately bring their innovations to the marketplace. Established companies, too, benefit from collaborating with nanofabrication facilities, leveraging their cutting-edge capabilities to develop next-generation products and maintain their competitive edge. By partnering with these institutions, companies can access the latest research findings, specialized equipment, and highly skilled personnel, accelerating their own research and development efforts. The existence of a robust network of nanofabrication facilities is essential for fostering a thriving ecosystem of innovation in nanotechnology. By providing open access to their resources, promoting collaboration between academia and industry, and training the next generation of scientists and engineers, these facilities play a vital role in ensuring that the nanotech revolution continues to accelerate, bringing forth transformative technologies that benefit all of humanity. The future of nanofabrication facilities lies in their ability to adapt to the ever-evolving landscape of nanotechnology. As new materials are discovered, new fabrication techniques are developed, and new applications emerge, these facilities must continuously upgrade their capabilities, expand their expertise, and foster new collaborations to remain at the forefront of innovation. One exciting trend is the development of mobile and modular nanofabrication tools that can be deployed in a wider range of settings, making them more accessible to researchers and entrepreneurs who may not have the resources to build or access large centralized facilities. This democratization of nanofabrication has the potential to further accelerate the pace of innovation, empowering individuals and small teams to make significant contributions to the field. As we venture further into the realm of the infinitesimal, the importance of nanofabrication facilities will only continue to grow. These cathedrals of innovation, with their gleaming instruments, brilliant minds, and collaborative spirit, will continue to serve as the crucibles in which the future of nanotechnology is forged, shaping a world where the seemingly impossible becomes possible, one atom at a time. As we've journeyed through the exciting world of nanotechnology, we've witnessed its transformative potential to revolutionize the semiconductor industry and, in turn, reshape our technological landscape. From high-temperature electronics that operate flawlessly in extreme environments to energy-efficient hardware systems that minimize our digital footprint, the possibilities are as boundless as the nanoworld itself. But this is just the beginning. The breakthroughs we've explored are but a glimpse into the future that awaits us, a future where nanotechnology empowers us to create a more sustainable, connected, and equitable world. As researchers continue to unravel the mysteries of the nanoworld, we can expect even more astonishing discoveries and innovations that will redefine what's possible. So stay curious, my friends. Delve deeper into the world of nanotechnology. Explore its vast applications, engage in the conversations surrounding its ethical implications, and contribute to its responsible development. The future is not something that simply happens to us. It's something we create together, one atom at a time. If you found value in this video, don't hesitate to show your support by hitting the like button, subscribing to our channel, and sharing this content with your network. And remember to ring the bell icon to stay updated with our latest insights and offerings. Your engagement fuels our mission to empower businesses like yours. Thank you for being a part of our community.